Welcome to our presentation entitled Retrograde Reef Accretion Caused by Hurricanes and Sea Level Rise. I gave this talk at the National Coral Reef Congress in Mexico in 2017. This was Discovery Bay in Jamaica in 1972. It was the epitome of a Caribbean reef completely covered with dense thickets of aquaporid corals. The pioneering studies which described its ecology led both ecologists and geologists to make the general assumption that what you see on the reef surface is what you get inside the reef. In other words, the internal reef framework reflects the community above it. In 1980, the reef was decimated by Hurricane Allen. This was the most intense Atlantic hurricane ever recorded. It was a Category 5 storm with 310 km/h winds and 15-meter waves, and it obliterated all corals down to 10 meters. And as you know, it failed to recover, and it still looks today like it did after Hurricane Allen. So this raises an important question. How many times is a reef decimated by big hurricanes? And how does this affect accretion over thousands of years? From this we can formulate a hypothesis. If reefs are regularly destroyed by hurricanes over thousands of years, their accretion will be controlled by clast accumulation, not framework growth. And it's important to test this hypothesis because we need reliable models of reef accretion to predict the impact of sea level rise on reefs and their coasts. So can healthy reefs keep up with sea level rise, and can they continue protecting our coastlines? To test the hypothesis, we analysed geological data from a 4-kilometre long reef off Punta Maroma between Puerto Morelos and Playa del Carmen. This reef had a clear zonation, with each zone separated by slope breaks. You can see that the crest line marks the centre of the reef deposit and separates the back reef from the reef front. The reef front extends to a depth of about 6 metres and is composed of two zones. The stump and boulder zone forms closest to the crest line, and a little further downslope we've got the spur and groove zone. The reef front terminates at a slope break, and then you pass out of the reef deposit into a flat bedrock terrace. And this terrace terminates in the middle of the shelf with another slope break called the mid-shelf break. Now when you trace these zones laterally, you see two interesting features. First, the crest line is a uniform distance of about 300 meters from the slope break at the edge of the rock terrace. And secondly, the width of the reef front decreases about 100 meters down the reef, and it shallows from about 8 to 3 meters as you go from north to south. If we take a closer look, you can see that the decrease results from the disappearance of the spur and groove zone to the south. Now, to investigate the geology, we drilled a 12-core transect down the reef front. And you can see cores 1 and 2 recovered the bedrock from the underlying Pleistocene terrace, but the rest of the cores were all composed of large acroporoclasts with rare in-place colonies. In core F6, these clasts sit directly on the bedrock, but in all others, they're underlain by unconsolidated sand and gravel. So in other words, the coral clasts form a thin layer over unconsolidated sand. This cross-section shows that the reef nucleated about 5.5 thousand years ago, approximately 3 meters below present sea level. And from that position, it extended in both directions as sea level continued to rise. But most of the extension occurred in the landward direction, and the reef slowly retrograded over its back reef over a 5,000-year period. Now, in all the cores with 2 dates, there are age inversions, and there are age inversions between cores, and these inversions are all consistent with a structure composed of clasts, not of coral framework. Okay, so we have a puzzling range of findings. Why is a crest line a fixed distance from the mid-shelf break? Why does the reef thin to the south? And why is it form of clast and not coral framework? And why is it retrograded through time? Well, the answer is hurricanes. This is a model of how hurricane waves control reef development. Before the hurricane, acropora forms dense thickets like it did at Discovery Bay in the 1970s. Now, during hurricanes, if you calculate the breaking depth of 15 to 20 metre waves, they break in 12 to 15 metres of water, not at the crest line. This breaking depth coincides with the mid-shelf break. So waves hit the slope break, they plunge onto the rock terrace and they destroy the acroporas. And since they all break from the same point, they will deposit clast at a fixed distance from that point. So this explains the 300 metre distance between the crest line and the slope break. Now after the hurricane, the reef recovers to its pre-hurricane state within a few decades. But there's good evidence to show that big hurricanes recur every 150 to 300 years. So this will result in a growth destruction cycle, so that if you have a 6,000-year reef, it'll have undergone between 20 and 40 cycles of growth and destruction. And this explains why the reef is composed of rubble, not framework. Now, what about the retrogradation? Well, hurricanes aren't the only geological process to affect reefs over the last 6,000 years. Sea level's also risen about 3 to 4 meters in that time. Now, rising sea level causes hurricane waves to break higher on the slope break, and so less energy is dissipated. In other words, the slope break provides less of a barrier to the wave as sea level rises. So the wave increases its energy and it's enabled to transport clast further upslope, and over time, the crest line retreats, causing retrogradation. But what about the longshore changes? Well, not only are clast transported upslope, but they're also transported along the reef because hurricane waves usually come in at an angle. So after each big hurricane, you'll get a progressive migration of the crest line along shore. So one end will be older and has had time to develop spur and groove, and the other end will be younger and has not had time. So is there evidence that supports this model of hurricane retrogradation? Well, in this shot, taken shortly after Hurricane Ivan in 2004, you can see fresh clast of acropora forming a talus slope into the back reef and encroaching on the head coral. But just a short distance away, we find one that's been completely engulfed by clasts, almost buried alive. And this is clear evidence of retrogradation. Lastly, here's a shot of the reef crest at Discovery Bay 36 hours after Hurricane Allen hit. This is where all those iconic thickets of acropora ended up. But Woodley later went on to report that in 1988, Hurricane Gilbert carried this rubble farther into the lagoon. So this again supports the retrogradation model. So what can we conclude from this model? First, what you see on the reef surface is not what you get in the interior, unless the reef just got destroyed by a hurricane. And secondly, processes occurring during hurricanes control fringing reef accretion over geological time, not framework growth. So we need to reassess our ideas about how reefs will respond to future sea level rise.